Welcome everyone to the Spectral Geometry and the Cloud seminar. Today we have Julie Rowlett, and the topic will be spectral invariants of integrable polygons. The virtual floor and the real floor is yours.
Thank you. Thank you so much for inviting me back here. Hello to everyone out there. I have seen many familiar names, so hey. And I'm going to be talking about joint work with Gustav Nordell, who's also here digitally in the audience. And right in the beginning, I'd like to tell you that all of your questions are welcome. All questions are good questions. So feel free to speak up if you wish, but you can also use the chat function and either send to everyone, or if you're shy, you can send just directly to me, and I'll answer your question without revealing your identity. Let me start with, what is an integrable polygon? I know one person in the audience knows, but let me give a definition for everyone. So, and let me give you actually first a little outline. So first we'll start with some geometry primer. Then we'll talk about the heat trace. Next, we'll go into higher dimensions. And if we have time, I might say something about spectral zeta functions. Okay, so geometry primer. Integrable polygons just a polygon that has all interior angles. Of the form pi divided by a positive integer. Okay. So my first question for everyone, is there something we can immediately say about their geometry? Like, boom. With this definition.
They'll be convex.
Yay, good job. So it follows then that they are convex. Now, why is that? I think it was Jean who answered, right?
It was.
Yes. So why did you immediately know that?
All angles are smaller than pi.
Exactly. So a non-convex angle is an angle that's bigger than pi. So we can't have those. So we immediately know that all integrable polygons are convex. Okay. So let's now determine what they are. I'm going to call this a proposition, and it's super classical. And we're going to determine what they are. But to make it kind of fun, I'm not going to tell you immediately what they are. We're going to figure it out in the course of the proof. Okay. So we know that they're convex and they have some number of sides. Let's call the number of sides n. So what do the angles add up to? You can also answer questions in the chat, by the way. Come on, I know some of you know this. Yes. Okay, Genkai, who's in the actual audience, says n minus 2 times pi. Exactly. Okay. So now, if we know that all the angles are at most pi over 2, then we get that right? Pi over 2 times n. Well, that's as large as the sum of the interior angles of such a polygon, because it's pi divided by an integer. So the largest any angle can be is pi over 2, but they could also be smaller. And so the largest the sum of the angles of an integrable polygon can be is pi over 2 times n, right? And then the actual sum is pi times n minus 2. And so doing a little bit of algebraic rearrangement, we get that n is less than or equal to 4. So that tells us that integrable polygons can only have 3 or 4 sides.
Julie, we are in Euclidean space, right?
We are.
Because, I mean, there's a question in the chat, so asking if we're in hyperbolic space, so I assume we are in the
Yeah,
Euclidean.
sorry, I didn't see the chat just then. Yes, super. So we are not in hyperbolic space. Different things would happen there. Exactly. So we know that, okay, for n is 4, this has to be an equality, and therefore you get that it's a rectangle. So the integrable polygons include rectangles. And then triangles are the next option, because the number of sides is 3 or 4. So can you give me some examples of triangles? Yes. So equilateral triangles, because there all the angles are pi over 3. And then, right. So we also know that the angles of a triangle sum to pi. And so you cannot have a triangle with all of its angles less than pi over 3. So the only other integrable polygons that are triangles are going to necessarily have a right angle. And so then you just get a cute little equation to solve. Find all pairs of integers, a and b, such that 1 over a plus 1 over b is a half. Because you know it's a right triangle, so one angle is pi over 2. So the other two have to sum to pi over 2 as well. And then the only solutions with a and b positive integers are a is b is a quarter, or a is a third, and b is a sixth. So that means our integral polygons are rectangles, equilateral triangles. And I'll use this common, at least in the US, it's probably called them 45, 45, 90, and 36 to 90. And so now we have definitively identified all of the integrable polygons. Any questions?
Yes, why are they called integrable?
Ah, okay. Well, somebody called them that in the literature. And it's, as far as I could tell, the sort of oldest terminology. And it was someone studying, maybe Gustav remembers, I think their name starts with a G, and they were studying closed geodesics in polygons. And one of the properties of these four shapes is that they are the only planar domains that do something called strictly tessellate the plane, which means that they tessellate the plane by orthogonal reflection across the boundary faces, and in such a way that the lines containing the boundary faces do not cut into the interior of any of the copies. And so then if you draw closed geodesics in these types of polygons, they turn into, in this tessellation, like straight lines that go through the whole plane, if that makes sense.
Sure, yeah, thank you.
Sure. Thanks for asking. Any other questions? Okay, good. Then let's get to section 2, which is features. So I will mostly be considering we'll be considering both the Dirichlet and the Neumann boundary conditions. So I'm just going to really so we could have a domain like this, which is not an integral polygon, as we can see. So we will be considering just general polygonal domains as well. And we'll also be thinking about smoothly bounded domains. But we'll always have a bounded domain or something compact in higher dimensions when we get there as well. And so this is spectral geometry in the clouds. You guys all know this, but we're just going to write it down for completeness anyways. So we have our Laplace equation, we're solving inside the domain, and we're setting either the Dirichlet boundary condition or the Neumann boundary condition. And then we get, I'll take my Laplace operator to be minus dx squared minus dy squared, so that our eigenvalues are negative. And in this setting, when we're in 2 dimensions like this, then we know the asymptotics of the eigenvalues is that they grow on the order of k. Okay, since we're in dimension 2. So we can put together the heat trace. I'll call H omega of T. And that is sure, let's do this. Leave the microphone to KT. And this is now fantastic for any t greater than 0. Because of the rate at which these tend to infinity, we have beautiful convergence for any t positive. Right, okay, so now I'm going to give you a theorem, which is not ours. It's from the 1980s, and it's by Vahnberg, who I don't know if is in the audience, but there are other people in the audience who know him. I've seen, and you probably know this work. And it says the following thing. So now, instead of an integrable polygon, just assume we have a convex polygonal domain. Then for the Dirichlet boundary condition, one has the following expansion. So you can see if t goes to 0, the sum is going to diverge, and it diverges in a very specific way. So the leading order term behaves like 1 over t with the area divided by 4 pi as the coefficient. And then the next term, because it's a Dirichlet boundary condition, is the length of the perimeter divided by 8 square root pi t. And then we have the sum over the angles. So if it's an n-gon, let's say it's a, change that right here, n-gon.
Julie, there's a question in the chat again.
Yes, okay. Oh, Zeev, hello. Well, this part comes before Vahnberg and 3-second Raja. That is absolutely correct. But what I'm gonna write next is these two. Okay. So what they proved is that the remainder is O of e to the minus c divided by t, and they proved an estimate for the c. So they can say c is greater than or equal to a certain quantity, which is kind of a messy geometric thing, so I don't feel like writing it. I'll leave you to look at the paper if you want to know exactly what stands there. So this fact was conjectured previously, and then they proved it, and they proved the estimate for the rate of rapid decay of the remainder. So that's why I'm quoting them. Does that make sense? Okay. And so let me mention two things. The first thing is that this is not known, as far as I am aware, if you change the boundary condition to Neumann or say Robin. So I believe that for both Neumann, Robin, and mixed, this is open, and I've started working on it with Gustav and Simon Larson, both of whom are my colleagues here. So we think we can generalize to these other boundary conditions.
Julie, may I ask a question?
Pardon?
May I ask a question? It's Simon.
Of course, yes.
I think this is known for the Neumann case.
Ah, okay.
Perhaps not an explicit remainder, but the exponential decay.
Yeah, I was a little bit unsure of that too, because I was looking through Vahnberg the other day with Gustav, and my recollection of, did somebody do it maybe not as cleanly?
That is true, but it's also contained in one of your papers on manifolds.
Okay, so
Neumann, it's known with a non-explicit C.
Right. Okay. Okay.
For Robin, it's false.
For Robin, the decay is false?
Yeah, you have another constant order term.
Oh, of course. Yes, 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 yes. Exactly. We do have another constant term for Robin. So let's go like this. Okay. For Neumann, known but I'll write it this way. An estimate for the C is not known. Thank you for pointing that out. Okay. So Vahnberg has himself said that the estimate that they obtained for the C does not seem to be what one would expect heuristically as the sort of lowest value of, or largest value of C such that this holds. So it's been something that people have thought about. Well, what is this optimal C? And we can calculate it in the case of these integrable polygons. But this was also in some of these cases previously done in the thesis of Vahnberg. So I'm going to quote him. And we have some different ways of calculating, but you can find this as well there. The year is something like 2015, I believe. The optimal C being is L squared over 4, and L is the length of the shortest closed geodesic in your polygon. So basically you have such an estimate for L squared over 4 plus epsilon equals C for any epsilon greater than 0. And if you want to be more sharp, then you actually can calculate higher terms in the expansion. And that remainder term is either going to be e to the minus L squared over 4t divided by t, or divided by the square root of t, depending on which polygon it is. So that in and of itself is kind of an interesting fact. Okay, so what is the shortest closed geodesic? That's perhaps interesting. So if we have a rectangle like this, then you have a whole family of shortest closed geodesics of length 2a. And then if we have a equilateral triangle, the size of length L, Then we join the midpoints of the sides. And we get something known as a Fagmano triangle. And that is the shortest closed geodesic. And it has 3L/2. And for the other two, the shortest closed geodesic is an altitude of the triangle. So in this case, it goes from the right angle to the hypotenuse and back. And it has length √2a. And I should note that because this is a right angle, there is a well-defined law for calculating how an incoming geodesic leaves. Because you can essentially flip it out and then use the law that we know for how geodesics bounce off of flat boundaries. So, and then for the last one, if it's basically half of this equilateral triangle, then it's
So, Julie, I have a naive question.
yes.
So, the shortest geodesic is sort of like the systole in a closed Riemannian manifold. Do you know if
Yes.
there's a link between the systole and the heat trace on closed Riemannian manifold?
Well, on flat tori.
Okay,
Right.
yeah.
And that actually is a big motivation for how the proof works. So you definitely have this connection for the same kind of statement for flat tori. And I would guess that probably for flat space forms, you should also have something like this.
Thank you.
Yes, thanks for asking. Right, so that's this is the shortest closed geodesic. Okay, so then that gets me over to the proof.
Excuse me.
Yes,
So this statement is for both conditions, Dirichlet and
yes, actually, yes, exactly. Yes. It holds for both conditions.
okay.
Yes, thank you. So, how does one prove this? How would you do it for a rectangle? It's fun to be in this room because it's actually like, these are the rooms where I teach students to calculate such things. So for a rectangle, they will learn to calculate all of the eigenvalues explicitly. Right at lambda n, because they usually have two parameters. Okay, so we calculate, and in some instances, correct or complete some of the calculations that were in the literature. So for example, for a rectangle, this is very classical. It goes back hundreds of years. I'll just write it down for the Dirichlet boundary condition. So you separate variables, you have two one-dimensional problems, that turns into calculus. Basically, you solve them and you get these values, and then you use something a little more fancy to be able to compute that you actually do end up with all of the eigen values, because the eigenfunctions you got are complete in the sense that they span L2. Okay, so that means we can write down the heat trace explicitly as this double infinite sum. The equilateral triangle, it gets a little bit more interesting. So you have this expression, and now the values m and n are in integers. And if you see this expression without the following 4 conditions, it's wrong. So, and actually Verhoeven proved that. So that's kind of cool. He proved that if you don't impose any further conditions on the m's and the n's, these cannot be the eigenvalues of any bounded planar domain. Essentially what goes wrong is, the Weil asymptotic has to hold, and if you don't impose restrictions on these, then it won't. So the restrictions are, you need m plus n is congruent to 0 mod 3. And you need m is not 2n. N is not 2m. And m is not minus n. And you can see this, so if you look, there's an expression for the eigenfunctions, which is a sum of complex exponentials, e to the I times some pi times something involving m and n, and then your, x and y. And A guarantees that the boundary condition holds. So you can prove that it's necessary and sufficient for this to imply that the function you cook up, basically by doing reflections, will satisfy the boundary condition. At the same time, when you have this kind of not super obvious linear combination of trig functions, it could be that the whole thing just collapses and is 0. And as we all know, 0 can't be an eigenfunction. So that is what the last 3 conditions guarantee. And so we wrote it out in a maybe more transparent way than has appeared previously in the literature, that these are necessary and sufficient to guarantee that the function is actually an eigenfunction. So, and then there's also closed expressions for the other 2. And so for the isosceles right triangle, you get pi squared, m squared, n squared, or a squared. And there, the restriction that you need to have is m is greater than n is greater than 1. And we didn't figure these out. These are all known in the literature. And then for the 30, 60, 90, it's 16 pi squared over L squared. I feel like I'm missing a 9. I could be missing a 9. Just put that in question. M squared plus mn plus n squared. And you have the same restriction on m and n. You can find this in the papers of Brian McCartan, and this one, a good reference is Cutler and Situito. So we have explicit expressions for the eigenvalues, and that means we have explicit expressions for the heat traces. And they look like e to blah, blah, blah times t. So how do we get a sum that looks like that with the t in that position to change so that we have t in the denominator? I'll write a hint that I know at least one person in the audience will understand. Now, you know what this means, but think about it en français. Yes. Oh,
Poisson.
exactly. This is a Chinese fish, but if we instead say the word fish in French, we get the poisson. And so you use Poisson summation to rearrange your heat trace, and then it just more or less falls out.
Not poison.
Exactly. So that's the essence of the proof. Questions? One thing I should mention to be careful about is with these eigenvalues of the equilateral triangle, when we write them this way, there are 6 pairs of integers that will satisfy the 4 conditions and give you the exact same eigenvalue and the exact same eigenfunction. So when you're writing something down like the heat trace, you have your sum over these with these conditions, and then you divide it by 6. If there aren't more questions, then I'm going to.
And
Sorry, may I ask a question? Yeah. So what is the highest multiplicity of these eigenvalues?
The highest, well, for the equilateral triangle, I've computed that, well, of course, we all know the first eigenvalue is simple. The second eigenspace has dimension 2. And for the others, I haven't calculated, but I believe there are some conjectures about what the multiplicities can be. Did that sort of answer your question?
Okay, thank you. Thank you.
More questions?
Oh yeah, I meant to ask if, so you said that you had 6 different values for the integers and therefore you have to divide by 6. Is it every single term appears 6 times or most terms appear 6 times, so it works to divide by 6 on average?
So the thing is, this comes from an expression for the an associated eigenfunction. And in that eigenfunction, you can sort of cycle m and n, given an m and n, you create a little orbit of like switch m to like the n slot and then make the n into a minus. And so there's sort of 6 little tweaks you can do. And when you do that, the eigenfunction stays the same. So it's telling you that those 6 pairs of values of m and n, and also you checked, and we did it, that when you have a pair, m and n, that satisfies these 4 things, and you do this little orbit of the other 6 pairs that give you the same value, everybody else in the pair will satisfy these 4 conditions as well. So it's telling you that that one eigenfunction, when we list the eigenvalue like that, its eigenvalue would be appearing exactly 6 times. And then when you have a different orbit of M and N, it is a different eigenfunction. And so even if it had the same value as another one, since we count eigenvalues with multiplicity, it would get repeated because it has a linearly independent eigenfunction. Even
But
if
is
the value.
there like exceptional values for which the orbit is actually smaller? Say you said you switch n and minus n, for instance. Well, if n is 0, then that doesn't do anything.
You can, the precise details of how you switch it, it's probably easiest if you just look in our preprint. But if these four conditions are satisfied, then you're not going to sort of have any collapsing down of the orbit. If that makes sense. Like there will be exactly 6. Yeah. Okay.
Yeah, if I may, one comment about multiplicities. These are all known. It's like it's similar to the case of the rectangle, where the multiplicities are the number of ways you write an integer as a sum of 2 squares, and that's something that is now understood and is unbounded, but is very irregular as a function of the energy.
Mm.
And
Right.
the same thing happens for the equilateral triangle and the other integrable triangle. It's just a little bit more complicated, but it's essentially like a divisor function. It's a very arithmetic thing, but it is definitely not bounded.
So the multiplicity, right, but it's probably not that easy to say, well, the 4th eigenvalue has multiplicity exactly 3.
No, that's not something that's in the cards. It's like asking what is the number of divisors of the nth integer. It is a function, but you can't write down any closed form.
Right. Exactly. Okay. Thank you. But since you do have formulas, so if you wanted to, you could calculate, for the first, well, the first we know, the second and the third, you could start doing that explicitly since you have formulas. And you could write a program to do it. I'm not sure how interesting it would be, but one could do that. Okay, so now I'm running out of time. So let me just say something then very briefly about smooth boundaries and higher dimensions. Now I'm just going to assume that these are convex polygons and nothing else about them. Okay, so they're convex, and I'm assuming that they're converging in Hausdorff to a smoothly bounded convex domain. Then the first 1, 2, 3 heat trace coefficients. So these are the coefficients in the short time asymptotic expansion of the heat trace. The first 3 converge to those of the smoothly bounded domain. And this heuristically really goes back to Katz's paper. So there are some things, Katz was very honest about, you know, in case anybody doesn't know, can one hear the shape of a drum? Katz was very honest about not doing things rigorously, but wanting to do them more heuristically. But some things he did rigorously. And anyways, you can make everything rigorous. And essentially, it goes back to that paper that the first three heat trace coefficients in this context will converge to those of the smoothly bounded domain. But the domains that are converging are smoothly bounded and converge in Hausdorff to a polygonal domain. Then only the first two. So that's just kind of a fun fact that in a certain sense, at least from the heat traces perspective, the convex domains approximating a smoothly bounded one have more convergence of the heat trace coefficients than the other way around. So that's just a comparison. And of course, for a smoothly bounded domain, you do not have such an exponentially decaying remainder term, because the next terms in the heat trace, for example, there's a term with a square root of t, and the square root of t term is basically integrating the curvature over the boundary in absolute value squared with some coefficient. And so that thing won't vanish. And so, yeah, the heat trace just looks quite different compared to things with flat sides. So the last thing I'm going to get to, so I'm not going to get to the spectral zeta functions, but you can look in our preprint if you want to know about those. I want to just tell you something about what's happening in higher dimensions. And then we can have some more discussion. So this we proved together with some other talented students, Max, Blom, Henrik, Nordell, Oliver, Thim, who's now doing a PhD in physics, and Jack Vahnberg. And it says that now I have a polytope. So a polytope in 2 dimensions is a polygon. A polytope in higher dimensions is just a bounded domain with flat faces. A priori, no more geometric assumptions made about it than that it is bounded and has flat boundary faces. Then the following are equivalent. The first Dirichlet eigenfunction and we may say first because it is unique up to multiplication by scalars, is entire. So it is an analytic function in the whole space, not just inside the domain. And that's a non-trivial or obvious thing because in general, an eigenfunction could have yicky behavior at a corner similar to the way a Bessel function of a non-integer order has non-smooth behavior at the origin. So that's saying something. The second equivalence statement is that omega strictly tessellates the space. And the third is a sort of algebraic statement, and that is saying that omega is something called an alcove. I'm not sure if this was introduced before Berard, but it's thanks to the paper of Berard that we can say that if any of these hold, your polytope has a complete set of trigonometric eigenfunctions. So you can see from the example of 2 dimensions that having a complete set of trigonometric eigenfunctions is a rare quality because there's only 4 polygonal domains, 4 types that satisfy this. And they are precisely the 4 integrable polygons. So any other polygon has got to have some weird eigenfunctions that aren't trig functions. And the analogous statement holds in higher dimensions. So looking forward to higher dimensions, one thing that we plan to do is start calculating heat traces, for instance, and seeing what kind of terms we get. We reasonably expect the usual leading terms involving volume, n-1 dimensional volume of the boundary, and then the lower dimensional volumes of the various intersections of the boundaries, going down and down until you get a constant term, which would depend on all of the angles between the faces in your polytope. And then we reasonably expect also an exponentially decaying remainder term, probably with the same type of exponent. So I'll stop there and welcome further questions or discussion.
Thanks a lot, Julie, for this very nice talk. Do we have some questions either in chat or just unmuting oneself?
Yeah, can you say, Julie, can you say this theorem is for Dirichlet boundary conditions? When you say there's a complete set of trig eigenfunctions, you mean for the Dirichlet problem? Or is it something that you know for Neumann or Ben?
So exactly. So McCartan has written about this in 2 dimensions for also the Neumann boundary condition. But the problem, so I can't say this. These 3 equivalences, I don't know for the Neumann boundary condition. And I saw a colleague earlier who was here, Jonathan Rowlett from Stockholm. And we thought about this for Neumann. And the problem for Neumann that is not like analogous. So for Dirichlet, you know that your eigenfunction vanishes on the boundary, but not on the interior. And that's really essential to proving these equivalences, right? But for Neumann, you don't really have a replacement of that fact. So again, we're talking about the first non-constant Neumann eigenfunction.
Right. So you're saying that at this point you don't know what's happening in the Neumann case, let alone in the Robin case. But as you said, in 2 dimensions, there is something of McCartan, which I forgot exactly the formulation, but there is something that's not, maybe not an equivalence. I doubt an equivalence.
Exactly. Yeah, so in 2 dimensions, there's something known, but generalizing it in higher dimensions, I'm not yet sure how to do. It seems maybe feasible for Neumann. I mean, if you know number 3, then you have this conclusion here, thanks to Berard's paper. So Berard shows you, if you have an alcove, how to compute its eigenfunctions and eigenvalues. And I believe that Berard does it for both Dirichlet and Neumann.
Right, but I believe that Aubin hasn't been looked at.
No. I don't think so either. I think I don't think the arguments would work in the same way.
Yeah. Okay, thank you.
You're welcome.
And do we have any other questions for Julie?
Generally, what is the article?
It's a fundamental domain of a crystallographic Coxeter group, which is a thing defined in terms of a root system.
Yes.
And you know all about those.
I see.
Is this the same thing as what some would call a Weil chamber?
I think so. Yes.
Okay.
Right, because it's the Weil chamber. I forget if this is the right terminology, but you have a root system, and then you have the Weil chamber associated to the root system, and I think that's the same word.
Yes.
The Weil chamber is not compact, it's like a cone. But,
Yeah, right.
There's an affine root systems and so on. Some
Okay.
theoretical classification.
Thanks, Zev. All right, do we have any other questions for today? All right, well, I mean, it seems that there were a lot of questions during the talk and that they have exhausted the questions we had for Julie today. So let's thank Julie again for this talk and for giving us a proper board talk on this seminar. I think this is the first. And we'll reconvene next week with a talk by Irving Calderon, who will send us a title, I presume, in short time.
Welcome. Have a good week, everybody.